This video lecture is going to be a brief intro to LLVM, and in particular we're going to focus on the parts of LLVM that are going to be useful for us in our homeworks. LLVM is a fairly massive library that does a lot of different things. We are going to use it specifically for generating intermediate representations. So we're going to use it as a way to avoid generating assembly language directly from our abstract syntax trees. Instead, we're going to use LLVM intermediate representation, or LLVM IR, as the target of our code generation. And we're going to use the tools that come with LLVM to generate the x86 assembly code, and that's what we will execute. So when we are compiling our program, it's going to go and generate this LLVM IR, which then will get converted to x86 assembly. We assemble that x86 assembly into a binary. We run that binary, and that would be the executed program. So we're going to focus on the parts of LLVM that are particularly relevant for you when you're writing a compiler for Decaf. The main thing is to have these different global variables defined, and they're going to contain in them the LLVM IR that will be generated. So we're going to call LLVM functions, which will then store the LLVM instructions that we need for our input program. The first among them is the module, or called the module. Is just a convention. This is the name of the variable, so it can be anything, but it's a pointer to a LLVM module, and this contains all the generated code. So at the end of parsing, when we have done code generation for the entire AST, then we are going to print out all of the LLVM IR using this LLVM module pointer. Then there's the context, which is of this type, LLVM context. And this is useful in order to, as a variable that's provided to various functions, like, for example, the builder function. So this is a method used to construct the LLVM IR. And the builder is used, essentially it's the most useful part of LLVM for us is the IR builder. So this is the intermediate representation builder, and this builder is going to be a variable. So notice that it takes the context as an argument, and this builder is generally what we'll use to generate instructions in LLVM IR as we are traversing the abstract syntax tree. We need to make sure that the YAK actions incrementally generate instructions in the right order. Right? We want to, in the end, it's going to look like a sequence of instructions in LLVM IR. It's very similar to assembly. So we need to make sure that when we are producing these instructions, that we are linearizing our tree correctly. At the end of this process, we print out the LLVM output so we use the module, which is this variable over here, and we call the print function. And it's important that you print it out to standard error. And that's because in the programs that are provided to you, there is a program called LLVM run, which uses the LLVM pipeline to create the x86 binary. It assumes that your programs are going to produce the LLVM IR in standard error. So you have to make sure that you follow this convention so that you're able to use zipout.py and check.py correctly in the way that it's set up to be used. So let's start with some useful concepts and functions in LLVM. We will be using the types defined in LLVM. So the types are void, a 32-bit integer. A Boolean is represented as a 1-bit integer. A character is going to be a pointer to a sequence of characters which are represented as int 8. So it's 8-bit integer, and these are the valid types that we need for Decaf. So notice that it's returning a LLVM type pointer. Everything in LLVM is a instance of LLVM value. So that's something we can exploit. It's the type that will subsume all the types that we have to use in order to do code generation. So this one is just focused on types. This decaf type is not a LLVM data type, but rather your Yak program has to define it for all the types in a decaf program. So notice that it's just a variable that I'm switching on. It has different, it's essentially an enum type. You can define it that way. And each of the values that it has, we are using the builder in order to create a pointer to a type. Notice that this is the actual type value, right? So this is saying this variable is a integer, a 32-bit integer, etc. A constant in LLVM is, again, we're going to call different functions in builder. So a good way to get used to everything that's in builder is to actually look at the LLVM header file for the IR builder, which contains all of these functions. So you can get an idea of what are all the functions that are available in the header and in the LLVM library. These two functions here, getInt32 and getInt1, are ways to get a constant value. So in this case, the first one, getInt32, is 0 value, that's a int32 or integer, and the second one is a 0 value for int1, which is Boolean. So this is interpreted as false. Int1, a value of 1 would be true and a value of 0 would be false. If I want to do a string constant, so you can have string constants in decaf when you want to print out a string, then we're going to use this function, again in a builder, called createGlobalString. Notice that we can't create strings ourselves because we cannot allocate memory in decaf and create a string dynamically. So instead, we only have static or constant strings, and that's why we can represent the string as using this function createGlobalString. S here is the char star pointing to the value of the string constant, and there's often this argument to the LLVM functions, and that's just a name. So that global string that you can see there is going to be the name of this string constant in the LLVM IR output. So that's going to be the name. It's similar to a location, like in assembly, right? You would assign it to either the stack or the heap or a local variable of some sort. So this is just a name that's used to make the LLVM IR more readable. This is also a name. So this is a name for the pointer that I'm creating a pointer to this global string that's created by this constant get element pointer. So GEP stands for get element pointer, and get element pointer is one of these functions in LLVM API, which has quite a lot of description. So if you go to the llvm.org documentation and you look at get element pointer, there's quite a lot of explanation because it's a fairly complex function. For our purposes, though, it's fairly simple here. So this is GS, is this pointer to LLVM value. This is the first argument to get element pointer. And then there are these two zeros. So if you look at a string is nothing but a sequence of characters, and it's stored in memory somewhere. So there's a pointer to that first element. If I look at that pointer, what it's saying is I want to get the first element of, so when I have this pointer, so let's call it actually GS. Sometimes I want to increment GS before I even look at the value. Like if I have, for example, an array or a struct or something like that, get element pointer is used for all of those, anything that's laid out in memory. So the first 0 says don't increment anything, that's GS plus 0. And then the second 0 says I want the first element from that pointer. So that's why there are these two zeros over there. And the resulting pointer is stored in a variable called cast. And what we are returning from this function is this pointer that points to the first element of this entire string. So along with the length of the string, I can extract the entire string and print it out, for example. If I have a local variable, this is a useful helper function called define variable. It takes the LLVM type. Notice that I can get this by calling that function I defined a few slides ago, which gives me the Decaf LLVM type for any Decaf type. I get a LLVM type pointer from there. And if I have the identifier, which is a string, I'm going to store this variable in stack memory. So when I define a function or any kind of scope, I'm going to store the values of this onto the stack somewhere, so that when I call another function, I'm going to grow the stack and put in new variable values onto the stack so that they don't clobber each other, right? So this alloc a ints pointer is giving me a pointer onto the stack where I can keep the value of this identifier. And that's given to me by calling this function called createAllocA. One of the advantages of LLVM IR is we don't have to worry about whether it's more efficient to move this value into a register. So it does a register allocation for us depending on how many registers are available. So for x86, it knows how many registers are available, and wherever possible, it will promote something from being in memory to being in a register that is completely transparent to us. All we do is we call createAllocA and store the value of that. And here we're going to store it into the symbol table, and the symbol table is going to store these alloc_a ints pointers to each variable. And then it returns it so that it can be used elsewhere, as in like if it needs to be passed on to its parent, for example, in the Decaf AST. So that was defining the variable. If I want to use the variable, I access the symbol table and I look up the name of the identifier. I'm going to store, like I said, so remember I'm putting in a alloc inst a pointer into the symbol table right here. When I extract it out, I'm going to get a LLVM value pointer, just because that's a more generic way I can store anything in the symbol table. I do a create load. So when let's say I have a variable b, what I'm going to do is I'm going to look up in the symbol table where was the allocated space for this variable b. And then when I want to use it, I have to create a load. So something has to load that before I can use it. So for example, if it was in memory, I have to load it into a register before I can do something with it, like addition, or even if I want to take its value and assign it to something else. In fact, that's the case I'm going to look at next, which is assignment and checking types. So let's say I have an assignment here where I'm taking the value of b and assigning it to a. One of the things we need to do in order to be semantically valid is to check if the type of the L value a is the same as the type of the R value b. So L value and R value is just short for left hand value and right hand value. So in the grammar, I have this as my grammar rule, where I have TID and then TAssign, which is equal to, and then on the right hand side of the assignment operator is any kind of expression. This is a very simple expression, but could be very complex. So on the left is the name to which I want to assign the value, and expression is the R value. The R value is, we are going to take its value, whatever the expression is, and we need to put it into the symbol table under name. So what we're going to first do is, because we have defined this variable before, we must have defined a somewhere. Therefore, it must exist in the symbol table. And we look up name in the symbol table and we find the location where its value should go. So that's where, for this variable a, is this alloc a tells me where the value should go. The next step is to take the R value and use, so notice that what I'm still trying to do here is check that the types are the same, because I don't want to assign take a integer value and assign it to a Boolean. That should be a semantic error, so I need to check the types. So in this case, check the R value. This is the R value. I get its type and I get a pointer to this so that I can get a pointer type pointer. And this is going to be a pointer to the type of the R value, in this case, whatever the expression would be computed. And this sort of if statement here is a check that checks whether the R value type and the type that I have stored for this variable A in the symbol table, are they equal? If they are, then I create a create store function which takes the R value and puts it into the alloc A. Alloc A is here just a variable that is the location where I'm going to store the value for this variable A. So the next time I want to look up the value of A, I would look at the symbol table. It would give me this new value, right? Instead of the value that was there before. The next thing we want to look at is declaring a function in LLVM. So in order to declare a function, you have to create a type for the function. So a function is no different from a variable. It's also defined by a identifier, right? So that's why I'm going to store it in the symbol table, just like I would store a variable. So this is the name of the function. And then this func here is going to be, instead of a location for a function, because functions don't really have a location, you don't assign things to a function. What we store in the symbol table is the type of that function. So what is the type of a function? Well, we need to know what its return type is going to be. So this return type here, notice we're calling the same function we defined before, get LLVM type. We give it a return type. Let's say that it's, void type. Then it would give me a LLVM type pointer that refers to the void type in LLVM type definition. And the next thing I need to know is the arguments for this function. Each argument of this function will have its own type. So let's say I have func and then a int and maybe b bool, and it returns, let's say it returns an integer. I don't care what's inside the function at this point. All I care about is what is the name, what are its arguments. So there's two arguments, one called a, one called b. What are the types of those arguments? The first argument has type int, second one has type bool, and the return type is an integer. In this case, what I'm going to store in the symbol table here is a signature of this function. So when I store foo in there, I'm going to store what is its return value, what are the types of each of its arguments. And so when I have each of these individual types with me, then I can call the function create function from LLVM, and it takes the return type, the arguments. You can ignore this, keep it the default as false. We keep this default as external linkage as well. We use the name, right, of the function, and notice that we are going to put this into the global variable, the module, because it's organizing all of these function definitions, etc., go into a single place from which we're going to emit all of the LLVM IR at the end of the process. So this is how we declare a function in LLVM. And this symbol table is the same one as we had before, and it follows the same rules as we would for storing information about any identifier. But for functions, we're going to store the function signature. In some cases, you might need to promote a type in LLVM. So if the variable is of type I1, int 1-bit integer or Boolean, but the function only takes I32 or integer, then I need to promote the Boolean to an integer because I want to coerce the type. And in order to do that, we can use what's called a ZX instruction. And the ZX instruction takes, so this is again the name of the variable that we're going to use, which takes a pointer to a Boolean and then says I want to extend this from a 1-bit integer to a 32-bit integer, which I can do because I'm not losing any information when I do that. And it's calling this create ZX function. The value I get back is this LLVM value pointer, which is the promotion of the Boolean to an integer. A very useful thing in LLVM is the concept of a basic block, and we're going to study basic blocks in a lot more detail when we cover code generation. Here I'm just going to cover the basics you need in order to get going with code generation. It will cover all of the sort of theory behind basic blocks and everything in subsequent lectures. Basic blocks, you are all familiar with it already. They're just the parts of the program which are needed for control flow, right? So when I need a new basic block, I will create, essentially I want to encapsulate a sequence of LLVM instructions, and I might want to skip over them, for example. So a good example is if I have an if statement and I have a conditional, I have an else statement and this part here. So all of these statements that are here in this part and this part, they have to be kept separate from each other, right? So this sequence of instructions and this sequence of instruction, we call these a basic block, because if the condition is false, I want to execute this basic block. If the condition is true, I want to execute this basic block. So I need to keep those sequence of instructions separate from each other. And that's exactly what this function does. It creates a basic block. It takes the context, which is the global variable that we use. It has a name as well called entry. And the interesting thing about this is that we can store entry into the symbol table as well. So the symbol table is doing a lot of work for us. It's also storing the locations of where these groups of instructions exist. And we're saving that into the symbol table so that we can access them. As we'll see, that becomes quite useful later on when we are doing code generation of various when the code generation gets a little bit more complex, it becomes quite useful to store these locations in the symbol table. Func is a pointer to the function in which you're creating this basic block. It could be any, so it could have been, if there were bare instructions, which Decaf doesn't allow, but if there were bare instructions, it could be like the module is where we insert these instructions. But since this if statement has to be inside a function, we're going to pass it the function in which I want this basic block. And then this instruction, also in the builder, is called set insert point. Every time I do another call to a builder, let's say I do builder.createLoad or something like that, those instructions will go into this basic block, so I can keep these instructions separate from these instructions. Right, so that's the main reason why we create basic blocks, is to encapsulate these instructions. When you generate the code for a method, we create a new symbol table for the local variables. We create a basic block so that all of the instructions for that function don't get mixed up with some other function. And then we set the insertion point so that we start generating the instructions for this function. And then we add arguments to the function as allocated on the stack, which we'll cover in the next slide. So let's say we have function parameters. So if I have func foo and I have a function parameter x of type integer, notice that I can actually assign it a value. So we need somewhere to store this integer. So it comes in as a parameter, comes in with a value. We can even reassign that value. So what we do is there can be any number of arguments for the function. So what we do is we loop through using a for loop. We go through each of the arguments in a function and we create entry block allocation, which is very similar, except it's a special allocation for function arguments. We get the name of this function, in this case would be x, and we know which function it is. And then we create a store. This is very similar to what we did before, except it takes an argument which is the pointer to the argument for this function. And then we add this argument into the symbol table. And the reason we do that is so that when we want to access it here and assign it, we are able to get the alloc A that we created from the symbol table and then assign it the value of this expression, which is in this case 1. There's a few sort of random useful tricks in LLVM. If you want to know the current function you're in, you can call getParent from your insert block. So if you know what your current block is, your basic block, you can call the getParent function and it will tell you what function you're in. And if I have an extern function, which we do in Decaf, right, we can define these extern functions. They look very similar to the function definition that we saw earlier. We just create the return type, its arguments. We definitely want external linkage because what we're going to do is call these functions by linking the standard library against our Decaf program. That will give us access to things like print state, printing out stuff is done in the standard library. So these external functions will also have a name. Extern definition is stored in the module like everything else. Modulus in LLVM is done using the create srem function. Again, it's in the builder. And one caveat is LLVM uses the C++ style modulus, so does Decaf. So make sure that when you do modulus with a negative number, that you make sure you get the right answer. In this case, it should get the same answer as you do in C or C++. So control flow in LLVM is sort of more advanced. So this is not something you will need to know for homework 3, but for homework 4, you will need to know it. So I'm going to cover it in this video lecture. You might have to come back and view this when you're doing homework 4. First notion is backpatching, and I'm going to cover backpatching in more detail in later lecture notes, but essentially backpatching is the idea that if I have an if statement, for example, it's not just in if statements, but it could be in many other scenarios as well. I have this block of instructions. Notice I had motivated the reason for creating a basic block by giving the same example, right? But the concept here is we need some kind of names for this. So if true and if false would be the name, and then there would be an end if. So this end if is the instructions that would follow the if statement. We create a new basic block called if true and if false and end. So let's just call it end here. The subsequent code generation now, I'm able to insert code into any one of these basic blocks, and I can interleave it based on how my grammar looks like. And when I call the code gen. So it can be used for cases like break or continue, short circuits, etc. So for example, if I break somewhere in this part, I know that I have to break out of the if statement, right? If I have a while loop, if I have a while condition, and I have a block of statements here, if I have a continue, I know that I have to go to the start of the while loop. So I need these different basic block names somewhere. So what we do is we create a symbol table, and the symbol table exists for code locations, and we store the basic block pointer against these strings like if true, if false, and end. So for while statements, you would need a different set of one like while start, while end, and so on, so that continue and break can go to the right position based on where these basic blocks are. And we store the location of the basic blocks in the symbol table. When we are setting up branching between the basic blocks, this is quite useful because I can create a conditional branch. So this value is the conditional value. And if it's true, it goes to this location. If it's false, it goes to end, and then it sets the insert point. Crucially, it sets the insert point to if true BB, which is the part of the basic block that handles the cases when the conditional evaluates to true. And then it goes to the if true block and does the codegen function. After the if statement, we continue with the end basic block. So we create a branch that goes to the end basic block. And now we set the insert point to end basic block. And then whatever comes after the if statement, we would generate code for that afterwards. And it would get, inserted after the if statement code gen is done. LLVM intermediate representation uses what's called static single assignment, and we are going to study static single assignment in great detail before you start with homework 4. But static single assignment is a concept which is useful in defining an intermediate representation, and LLVM has extensive support for it because it's kind of baked into the LLVM IR DNA, is the fact that it's using static single assignment. And the concept of static single assignment is that you never reassign a value. So whenever you assign a value, the L value is always a new variable. And this allows us great flexibility when it comes to code optimization. So LLVM by itself does all of the control flow using 5 functions. And so 5 functions are covered in the static single assignment lecture notes. But briefly, the idea is that if I have 2 basic blocks and they both feed into the same basic block, if the variable x1 and x2, we don't know which route I'm taking. I could be coming from here or I could be coming from here. So the 5 function says if I come from the left, I will take x1. If I come from the right, I will take x2. You don't have to worry about which branch you took. You can just continue to use x3 as this new variable, and x3 will get the right value via the 5 function. It will either get 1 or 2 depending on which control flow path we took, right? So we're going to use this idea actually, and I'll give you a specific example where the 5 function is quite useful. And namely, that's for short-circuiting of Boolean expressions. If you're writing LLVM code for short-circuiting Boolean expressions, you have to write this 5 function yourself. And the way that you do that is you call the create 5 function. And you say what is the type of that, how many incoming arrows going into this basic block, and this is the name that you're going to assign to it. So in the previous slide, it was x3 was a name, and I'm going to use 5al as a name here. And the type is an LLVM type, which is based on the incoming value from these 2 different control flow paths. So the add incoming functions so we're creating a new 5 function here in the current basic block, and it's saying it's coming from 2 different places. The current basic block, it's coming from up. So there are incoming blocks for this 5 function. So when I have a 5 function here, it's going to take value from one and the value from other. Depending on which path was taken, it's going to return the value that's then essentially 5al will get that value based on which control flow path was taken. It's incredibly useful for cases like this. So here's a more concrete example of that rather than an abstract one. So let's say I have a statement like this in Decaf, which is A or B. In this case, A is assigned to be true and B is assigned to be false. Notice what short-circuiting of a Boolean expression should do for you is, since this is an OR, if either of them is true, then the result is true. And we're going to evaluate from left to right. We look at the value of A. We know that it's going to be true. If it is true, there is no need to evaluate B. Right? That's what a short circuit means, because C is going to be true no matter what the value of B is. Whether B is true or false, we don't care. And this helps us save some computation. Like this B might be a function call to something quite expensive. So by short-circuiting this Boolean expression, we can maybe save a lot of computation time. If I look at the LLVM IR output for this, all of the variable init code was removed. So all I'm doing here is storing true in A. That's the location name for A. So this A is stored in %A. This B is stored in %B. It's stored for false. And then we load A1. So it's loading the value of A in order to check. So it's a Boolean. You can see that it's I1. It checks that value and says if A is true, then do not evaluate B. So let's see how it does that. So if it was true, then it goes directly to this basic block called short circuit end. And short circuit end has these 2 predecessors, no circuit and func, which is this initial block there. And short circuit end says, I don't really need to evaluate the B because A is true. So that's defined in this basic block. if A was false, then we still need to evaluate B, because if B is true, then we still return true. So that is given over here, where the OR is actually, this OR is done if there is no short circuit possible. Now, if you look at this, there's two possible values that you can have. The two possible values you can have is you don't do the OR, right? So this is going to be true. Then the value that I need to return if I ignore B is just this value A. So I look at a phi function. The phi function says if I'm coming from this basic block, which is function, which is over here, then I should use A1. If A was false and I actually had to do the OR, then the value of the OR is stored in the OR temp location. So if I come from the no circuit from this basic block, then I should use this one. So it either uses this one or this one, and the phi function decides based on which outcome was the case for this particular execution. And then it stores that and returns it. But essentially that's what the phi function is doing, is helping you figure out where the value comes from. Is it coming directly from here, or is it coming via this route, right? So the phi function helps you decide which value to take. There's one aspect of Decaf where we do allow backward function declarations. So in this case, if I look at this in function main, I'm calling test. Well, test is not yet been declared. So how does it know which function to call? So the way that we do that is we go through and we iterate through the functions, and we take each of these functions and store them. So main and test are all stored in the symbol table. And once they're in the symbol table, if I'm doing the code generation for main, I can actually look up in the symbol table and see where I have defined this function test. If it exists, then I can set up the code that would call that function, because I know what its return value is and I know what are the values, the types of each of its arguments. So I can create that and send it off to test. I create the code that would call the test function. And the trick here is to first iterate through the function signatures, insert them into the symbol table, and then generate the code for each function. Otherwise, you won't find test in the symbol table when you start generating code for main.